In this video, we're going to be looking at heat capacities, which is going to relate to phase change. We can think of water, but it applies, of course, to other things. So hopefully this Tobacco University video can help you better understand heat capacities. All right, so when we're looking at heat capacities in units, heat capacity is the ability of an object to store heat. An object's mass and specific heat primarily influence the heat capacity. It is typically measured in joules per gram or kilojoules per mole. You can see here some given values, and this kind of stepping stone gives you an idea of that lead and copper have very low heat capacities, low specific heat, compared to aluminum and water in comparison have much higher values for those. So when we look at our phase change graph here, looking at the heat of fusion, which is the melting phase. This is the amount of energy required to change a unit mass of a substance from a solid to a liquid at its melting point without a change in temperature. So it's kind of a hard concept. We're adding energy. We're not necessarily changing the temperature, because we think about water, it freezes at 0 degrees Celsius, or it also melts at 0 degrees Celsius. This heat of fusion, this melting phase, going from the solid to the liquid, the energy is used to break molecular bonds during the phase transition, do not increase the temperature, at least initially, referred to as latent heat. Now, if we keep adding heat, then of course, yes, that liquid will start to rise from 0 to 1 to 2 to 3 upwards in temperature, but during that actual heat of fusion or that melting phase, the temperature is flatlined here, not really changing, but the phase is. Now, heat of crystallization, or that freezing, the amount of heat energy released or absorbed when a substance transitions from the liquid, or sometimes a gas, to a solid crystalline state. So it's kind of like the opposite, melting versus freezing. Heat of crystallization would be this example. And again, using water, we might be familiar with the formation of icicles, or the very unique formation of these crystalline snowflakes. Now, melting and freezing are opposite, but also equal. Since melting and freezing are opposite changes, the amount of energy absorbed to melt a solid, in this case water, is equal to the amount of energy removed to freeze a liquid of equal mass. The heat of crystallization, remember that's freezing, is generally equal in magnitude, but opposite in sign of the heat in fusion, which would be your melting. So for example, when water freezes into ice, it releases heat. It's an endothermic process, and the heat of crystallization of water is approximately negative 334 joules per gram, or negative 6.01 kilojoules per mole, meaning 334 joules of energy is released per gram of water as it crystallizes. So again, melting process requires energy, freezing the process releases energy, going from our solid ice to our liquid water phase. Now, looking at the upper end of the curve here, we're looking at heat of vaporization or boiling. This is the amount of heat energy required to convert a substance from a liquid to a gas or vapor at a consistent temperature, typically at its boiling point. So in this graph example, it would be the horizontal line represented by the letter B here. This energy is needed to overcome the intermolecular forces holding those liquid molecules together, allowing them to transition into that gaseous state. So for example, the heat of vaporization for water at 100 degrees Celsius is approximately 2,257 joules per gram, or 40.7 kilojoules per mole, meaning that 2,257 joules of energy is required to vaporize 1 gram of water into steam. So it kind of gives you that kind of idea of the vaporization, again, going from that liquid to that gaseous state. So the opposite would be condensation, the amount of energy released when a substance transitions from the gaseous or vapor stage to that liquid at a constant temperature. So looking at our water, again, 100 degrees Celsius, the heat of condensation is approximately 2,257 joules per gram, meaning it takes that much energy is released per gram of water vapor as it condenses and slows down into that liquid water form. So again, things to kind of consider. Again, equal but opposite. So since vaporization and condensing are opposite changes, the amount of energy absorbed to boil a liquid is equal to the amount of energy removed to condense a gas of equal mass. But remember, those values will be essentially opposite. One will be positive, one will be negative. As we're going through that change, despite no change in temperature, we are having that change in phase.